Electromagnetic vertical launcher. An electromagnetic vertical launcher, we made the name up, includes an electric circuit with a 120 volt battery connected in series to a 100 ohm resistor, a switch, and a 500 gram 40 centimeter metallic rod. That's this guy over here. It is placed on two horizontal conducting supports so the current will flow through it. And it also has wires that are connecting it to these supports. These wires have negligible resistance, and we place the whole thing in a uniform 1.50 Tesla magnetic field. What else do I want to say about this? Yeah, the conducting wires here are, we talked about vertical, so obviously this guy is going to go up. We need it to stay connected into the circuit, and that's what these wires are for. And this tells us up is up and the horizontal direction is this way. A lot going on in this problem. First, find all the applied forces on the rod once the switch is closed. Assume the rod doesn't move. Find the normal force on each support when the switch is closed. What would be the minimum voltage required if we wanted to keep the rod weightless? The resistor is then replaced with the 5 ohm resistor. We're keeping the voltage at 120 volts. When the switch is closed, find the instantaneous acceleration of the rod. Then, if the rod moves 10 centimeters up, still remaining in the magnetic field and connected to the supports via the conducting wire, what is its velocity as it leaves the field? And finally, what is the maximum height reached by the rod? The magnetic field ends 10 centimeters above the initial position of the rod. On the diagram, show all the applied forces on the rod. First of all, we have gravity pulling it down, and you put that right at the center of mass. Each of the supports exerts a normal force. And then let's see what direction is the magnetic force. You use the right-hand rule. If the current is going this way, you put your fingers to the right, face your palm into the page, extend your thumb, and you find that the magnetic force is up. So here's our pseudo-free body diagram. Assume the rod does not move. Find the normal force in each support. We have our diagram here of the forces. And of course, if this were a free body diagram, we would just have a dot here and just have all the forces off of it. But we can certainly work with this. The acceleration will be 0 in the upward direction because it's not moving. So we do Newton's law. Sum of the forces equals ma. The right side will be 0. We have two normal forces. We have one magnetic force. And then we have gravity in the down direction. So now we just do some algebra. We find that the normal force is mg minus ILB, right? Because ILB is the magnitude of the magnetic force. And since the current direction is perpendicular to the magnetic field, the sine of the angle between L and B, the sine of 90, is 1, so that goes away, and we just have ILB. And what is current? Current will be the voltage, which is the 120 volts, over the resistance, and we just use this resistor because we're assuming there's no resistance here. We plug in all our letters, then we replace it with numbers, and note here we're going to use 10 for G. Yes, I know G is 9.8, but the AP exam does allow you to use 10, and it may make you feel bad because it's not 10, but it makes the math a little easier. And we get the normal force, and this is on each one, from each one of the supports to the bar is 2.14 Newton. Make sure you put the 2 there because there are 2 supports. What would be the minimum voltage required if we wanted to keep the rod weightless? So that means we don't have this battery anymore. We'd have to put in a different voltage source. So when an object feels 0 normal force, then it is considered to be weightless. So use the equation from part B, set the normal force equal to 0, and find the voltage. So here we go. Here's our normal force. We set that equal to 0. And let's see, we multiply through by 2, do a little rearrangement, plug in our numbers, and we get 833 volts. So if we applied that much, the rod would just be sitting here, not feeling any normal force, but it wouldn't start moving yet. It'd just be at rest. The resistor is replaced with a 5 ohm resistor. When the switch is closed, find the instantaneous acceleration of the rod. where the voltage, we're keeping it at the old 120 volts. We have a smaller resistor, so that will result in a current greater than what is needed to make the rod weightless. Hence, there is no normal force, and the increased magnetic force gives the rod an upward acceleration. So we started with this equation, and it's equal to ma because we know it's moving up. We're not going to consider the normal force. So acceleration is the magnetic force minus mg over mass. We substitute in again our values like we've done, put the numbers here, and we get an instantaneous acceleration of 18.8 meters per second squared. If the rod moves 10 centimeters up, remaining in the magnetic field and connected to the supports via the conducting wire, what is its velocity as it leaves the field? The reason this is so important, and especially this connected to the supports, we still need the upward force due to the magnetic field. And the only way you get that is if you have a current flowing in the rod. If not, then what happens to your acceleration the minute the rod breaks contact with the circuit? Well, your acceleration is negative g. But here we're using 18.8 in the up direction because we're still connected and we still have that magnetic force. We go back to kinematics. You never get away from kinematics, where the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times delta y, and the initial velocity is 0. So we substitute in our values, and here's the acceleration we found in the previous part of the problem. And make sure you change 10 centimeters to 0.1 meter, then take the square root of everybody, and the rod will be moving at 1.94 meters per second as it leaves the field. What is the maximum height reached by the rod? The magnetic field ends 10 centimeters above the initial position of the rod. So the rod leaves the field after traveling 0.10 meter. At this time, the only force acting on the rod is the gravitational force, where the acceleration is negative g. The velocity v0y leaving the field was found in part E. You will reach a maximum height when your final velocity in the y direction is 0. So here we go. We use third kinematics again, and we want to find where our final velocity is 0. We do a little algebra, and we find that the height, or the delta y, the height above the 10 here, you're over here, we just calculated this, which is 0.188 meters. So this is the delta y. But we want to find the max height above the circuit, so we left, let's see, so the h max is y0 plus delta y. We started at 0.10 meter with that velocity, right? This velocity here. We rose another 0.188 meters, so our final height is 0.288 meters. So that's measured from here to here, wherever we wound up. That's going to be the 0.288 meters.